Hi, welcome to Minds of Pint Einstein, the science show. My name is Marcus Chown. I'm a science writer. I'm the author of books like Quantum Theory Cannot Hurt You and my latest, which is called The One Thing You Need to Know. And it's my great pleasure to have with me today Valerie Jamieson. Now, she did a PhD in particle physics, and she spent about 10 years, or 20 years in fact, on the staff of New Scientist. But she recently had a career change, and she's now involved with the push to achieve nuclear fusion energy, to actually harness the energy source of the sun on the Earth. Now, there's been a lot of publicity about this lately, so I'm hoping that we can disentangle the reality from the hype. So welcome to the program, Valerie.
Hi, Marcus. Thanks very much for having me.
Well, it's really fantastic that you're giving up your time. Thank you.
So no problem. We go way back, don't we?
We do, yeah. We both worked on New Scientist many years ago. Well, you only a few years ago. But you grew up in Glasgow. How did you get interested in science in the first place?
Well, I loved science at school, and I liked maths, and I liked, in particular, physics. You know where you are with physics. That's the thing. You know, all those sort of questions about, you know, throwing a ball up into the air. You can calculate where it's going to land. I love that certainty. I mean, physics can explain why the sky is blue, but at the same time, those calculations that you do with Newton's laws, they can apply to the universe at large, can't they? And you can use them to predict that how the Milky Way is going to collide with its neighbouring galaxy in billions of years' time. So I love that idea of calculation and so on. And it was when I was at school that I got into the idea of particle physics. And I remember so clearly the first time I heard about particle physics, because it was the 1st of April, and I saw a show that was presented by Carol Vorderman and Frank Close. And Frank Close is a particle physicist, and he was talking about protons and neutrons, which I'd been learning about at school as part of my lessons on radioactivity. But Frank talked about smaller particles inside them called quarks. And these quarks had really funny names like up, down, strange, top, charm, and bottom. And they were all held together by gluons. And I thought, you're not getting this past me. This is the April Fool's joke. And I just remember it so clearly at the time. And it turned out it wasn't an April Fool. I heard Frank Close talking about particle physics again on the radio. He had written a book with Christine Sutton, and he was promoting that. And I just found this absolutely fascinating. You had to build particle accelerators, these giant machines and giant detectors to reveal what was really at the heart of the atomic nucleus. And I think that that difference in scale, there was something about it really captured my imagination. And my parents saw that I was really interested in this and bought me the book. And that was it. Kind of off I went, really. And so I did physics at school, loved that, and then ended up going on to do physics at university.
And you did a PhD in particle physics. Is it possible to explain what you did in a few sentences?
Yeah. Well, it was when I was doing physics at university. I suddenly thought, well, I love this particle physics, but you know, when I was at school, I thought, you can't be a particle physicist. I'm never going to be a particle physicist, am I? And it was when I was at university I realised, actually, you know, I'm kind of on that path. And I had the opportunity to go to CERN in Switzerland in between my 3rd and 4th years at university. And I went there and I learned about particle physics and just thought it was absolutely fascinating. So I decided to go on and do this PhD. And rather than work in Switzerland, I chose to work in Germany. And I worked on a new collider at the time, called HERA, and it collided electrons and protons. And what we were basically doing was using these electrons speeded up to the speed of light, and we used them like a big giant electron microscope to peer inside the depths of the proton and understand the structure of the proton in just exquisite detail.
And now, of course, now we've discovered that the proton and the neutron are fantastically more complex inside than we ever imagined. And they include all kinds of quarks. heavier quarks than we thought that they were made of. I mean, it seems to be getting more complicated, doesn't it? But you actually went on later to work for New Scientist for almost 20 years. What was the most exciting or interesting thing that you did during that period?
Well, I mean, obviously I got to work with great writers and like yourself, Marcus, and so that was.
I'll put the check in the post.
So that was a lot of fun. But being a science journalist, you'll know this, Marcus, it puts you in a really, really privileged position. Scientists are so generous with their time. You know, you just get to just pick up the phone and you get to talk to, you know, an astronaut or one of your science heroes. And I also got to travel the world as well. So I visited telescopes, you know, up in the top of mountains in Chile, for example, and in Hawaii. I went down to the bottom of a salt mine in Yorkshire where I was looking at dark matter detectors. I got to go to the Nobel Prize ceremony the year that Peter Higgs won the Nobel Prize for discovering the Higgs. And as a particle physicist and as someone who'd followed that story for many, many years, that was a real career highlight for me as well. So I just had a blast working at New Scientist.
Well, you didn't actually get hold of Peter Higgs, did you? Because he is famously elusive. Even on the day that he was awarded the Nobel Prize, he got on a bus from Edinburgh to Leith and hid in a cafe so that no one could actually get hold of him.
I did manage to get a selfie with Peter Higgs so at the Nobel Prize ceremony. At the time, it was no cameras, but I managed to sort of sneak mine in, and so we had a couple of selfies.
So now you've moved to fusion. Tell me quickly what your job is, and then we'll just get back onto the basics of what fusion is.
Yeah, so I manage something called the Fusion Cluster, and the idea is to bring together the right people and the right minds to get to fusion faster. Because as you said, we've been doing it for a long time and it's incredibly complex. It's too complicated for any one organisation to do on its own. So there are lots of people around the world attempting fusion. There's a whole new raft of startup companies as well that are getting involved. And the idea is to just really connect people and collaborate on the areas where it makes sense.
Right, so what is fusion?
Okay, so what is fusion? Fusion, well, it's as you said at the beginning, it's what powers the sun. The sun, of course, is this giant ball of hydrogen gas, and because it's so huge, you have this huge sort of inward pressure from the gravity. And what it's doing is it's squeezing those hydrogen nuclei together. They're coming together and they're fusing to create light elements.
So the nuclei are the cores of the atoms. You know, they're like tiny little planetary systems, you know, naively, with electrons orbiting like planets around the nuclear particles, which are like the sun at the center. And we're talking about the actual cores of these atoms.
Yeah, we are.
Yeah.
Yeah, because and what happens in the sun is that in the hydrogen, if you think about a hydrogen nucleus, it's positively charged. You've got lots of electrostatic repulsion, and you have to overcome that, which you can do in the sun. And you overcome that repulsion, and you bring those two protons together. And protons, of course, are the building blocks of all the elements that we know. So the hydrogens are coming together, they're creating lighter, other light elements. And in that process, energy is being released. So what we're trying to do here on Earth now is recreate that reaction. We're recreating mini suns.
Is there a simple way to explain why it's the gluing together of light elements that releases energy, and yet it's the splitting of heavy elements that also releases energy?
It's all to do with the nuclear force, and so you're not creating. You can never create energy. You only transform energy from one type of energy to another type of energy. And in what you're doing in both fission and fusion is you're just accessing those reserves of nuclear energy that are sort of bound up within the nuclei. And it all comes from that sort of rearrangement of nuclei. You get this energy released. And you get so much energy released because there's a little mass difference. And the equation everybody knows, E equals mc squared, that's transforming mass into energy. And the reason you get so much energy released is because the speed of light is such a big number.
So really, when you split a heavy nucleus or you glue together light nuclei, you end up with less energy per nucleon, per proton or neutron in both cases. So there's surplus energy left over, and that's what we're trying to, which ends up as I suppose the energy of motion, the kinetic energy of the fragments that are left over. Is that what?
Yes.
Yeah.
So in the fusion that we do, that we typically do here on Earth, we are using hydrogen fuel, heavier variants of hydrogen, and we're fusing them together. One of the most efficient fusion reactions uses deuterium, which is a heavy form of hydrogen. It's made of 1 proton and 1 neutron, and another even heavier version of hydrogen called tritium, which is 1 proton and 2 neutrons. And we're squeezing them together, and what happens is that creates helium and a neutron, and it's the neutron that carries most of that energy.
And the reason that we need to use that reaction is that the one in the sun is really inefficient and is far too slow.
And just as well, otherwise the sun would have burned out, wouldn't it? It would have used up all its fuel.
I think it's the fact that it takes 2 hydrogen nuclei 10 billion years on average to meet and stick that is the reason the sun takes 10 billion years to burn its fuel, and the reason we're having this conversation. But so the much faster reaction is this 2 versions of heavy hydrogen, the tritium and the deuterium, but that needs an even higher temperature than the sun. I think the sun's 15 million degrees. Doesn't this require about 100 million degrees in excess?
Yeah, that's right. So we need to get to temperatures of 100 million degrees or so, which has been done. So it's all about that. There are actually quite a few different ways of.
Yeah, but this is the real problem. It's you got to get to 100 million degrees without actually disintegrating or destroying your containment vessel.
Yeah,
that's the problem.
That's right, and it's done in this vessel that you see here. So I'm sitting inside something. Well, I'm not really sitting inside something called a tokamak, but I'm sitting in this donut-shaped vessel called a tokamak, and surrounding it are lots of magnetic fields. And when you heat these hydrogen gases to 100 million degrees, these kinds of temperatures, you end up with a soup of protons and electrons, all these just charged particles. And the great thing about charged particles is that you can use magnetic fields to direct them. And with the right shape of magnetic field, you can create like a sort of magnetic bottle. And so this charged plasma that's at 100 million degrees is inside this tokamak. On the outside of the tokamak, there are all these magnets. They create this magnetic field which holds the plasma in this donut shape, but it holds it so that it doesn't touch the sides. So we've got this donut-shaped plasma inside this metal donut, but it doesn't touch the sides.
Right. So really, the magnetic field acts like a kind of mirror. So these particles are flying around tremendously fast at 100 million degrees, but when they reach the edge of the magnetic field, they're actually reflected back in. They're just like a magnetic mirror. By the way, Valerie, how big is that tokamak that you're sitting in?
Yeah. So this tokamak here is the Joint European Torus, or JET. It's currently the world record holder in terms of fusion energy, and it's been operating for almost 40 years. It's 40 years old this year, and it's at Culham, and it's operated by a consortium of European physicists. And to answer your question, it's 3 meters in radius.
Right. Okay. Can we just backtrack one moment? And where do we get the deuterium and the tritium needed for this 100 million degree fusion reaction that we're all trying to, you're trying to create?
So bear in mind this is an experiment. Okay, so it doesn't. you don't need an awful lot of deuterium and tritium for this. Deuterium is quite straightforward. You can get it from water. So in a glass of water, there will be deuterium in there. So you can extract that from water.
I've got a glass of water here. I don't.
That's right. You are drinking tritium.
Are there a few drops of tritium?
So you're drinking a bit of deuterium in there. The exact proportion escapes me at the moment. That is
is it 1 in 5,000 hydrogen? Something like that. Yeah.
It's something like that. Yeah, I've got to admit the exact number sort of
when you think
escapes
of
me.
the size of the oceans, we know that we've got no problem with getting deuterium. But what about tritium?
Yeah, tritium is more difficult because it is radioactive and it's got a half-life of 12 years. So if I have a container like this of tritium, after 12 years, there'll only be half of it left. After 24 years, there'll be a quarter of it left. So it's a sort of depleting resource. For experiments like this, then you can buy tiny amounts of tritium, and experiments like this get their tritium from Canada. You don't need much for these experiments, but
they have a particular type of nuclear reactor that uses tritium.
That's right. Yeah, it's a kind of nuclear reactor in Canada that produces tritium, which we can then buy in tiny quantities and use them in these experiments. But when it comes to building fusion power plants, then we'll need more tritium, and this is the really smart bit about fusion. So if this was if this jet machine here was a power plant, on the outside of it, it would have a blanket made of lithium, and the neutrons coming out of the reaction hit the lithium, and there's a nuclear reaction that happens, and one of the products is tritium. So you're making your fuel. So you are you're just, it's self-sustaining. You're creating this fuel that then goes back into the reaction.
I can see a slight problem. And that is that there's a desperate need for lithium, because we have lithium iodide batteries in our mobile phones and things. Are we then? Is there going to be a problem finding enough lithium that we can turn into tritium?
So all the calculations show that there's actually plenty of lithium, and I think what's going to be really interesting is to see how this works out. So we shouldn't run out of lithium, but I think and I think in the context of electric vehicles as well, you know, obviously there are going to be a lot of people wanting lithium for batteries and so on, but there's also going to be lithium recycling as well. So the on the scale of things, fusion doesn't use an awful lot of lithium. There's some calculations show that it's the amount of water that you would have in a bath plus the amount of lithium you would have in a laptop would provide one person's energy needs for their lifetime. It really is, you know, quite small amounts. Obviously, you scale that up to a larger population, and that's more. But you know, compared with the amount of fossil fuels, and this is the big hope for fusion and why people are so interested in it. It's such an energy dense. It's the most energy dense form of fuel that we have. And what I mean by that is, if you just take 1 gram of hydrogen fuel that you would use in fusion, that could replace 10 tons of fossil fuels, 10 tons of coal. So we'd be taking that out. And we know that we need to decarbonize our energy. That we desperately need to do that.
So that puts it, you know, in a nutshell. This is an energy source that is pound for pound 10 million times as concentrated as the fuels we use, the chemical fuels like oil and coal. So I can understand why people are very keen to use it. Before we go on, you tell me about this development or breakthrough with the Tokamak and Cullen. There's another method that people are pursuing to fuse. Can you tell us about that, please?
Yeah, sure. So the thing you need for fusion, you need to get that fuel hot enough, you need it dense enough, and you need to bring it together for long enough. And that's something called the triple point. And it's a bit of a balancing act, because you can decrease the temperature, for example, that you need to achieve, but then you need to get the fuel denser. You need to have a sort of denser concentration of fuel. And that's the approach that's been taken at the National Ignition Facility, which is over in Lawrence Livermore Lab in California. And the approach they've taken is to take that hydrogen fuel in a tiny little pellet, and what they then do is they zap it with 192 really high-powered lasers. They zap it from all the lasers come in from different directions. And what that does is it essentially creates a shock wave which compresses the fuel, and for a really sort of tiny amount of time, but it makes it so dense that that fusion happens. And what was really exciting, they've been trying to do this for couple of decades, but at the end of last year we had a real breakthrough result when the National Ignition Facility, they demonstrated fusion, but what was really exciting was they got more energy out than they put in, and that's the first time we've seen that, and it's a huge breakthrough.
I think I read somewhere that the facility covers the area of about 3 football pitches, so that gives you some idea of how big these lasers are.
Yeah.
And the pellets, I think, aren't they the size of a peppercorn, something like that?
Yeah. So that's and again, remember, this is an experiment, and it was conceived decades ago. There's actually a really exciting startup fusion company that's about 11 kilometers away from where I'm sitting right now. It's up near Oxford Airport, and it's called First Light Fusion. And the core physics is the same, but instead of using all these laser beams, they use a shock wave that's produced by a projectile. So it's the same, do without those 192 lasers covering 3 football pitches. Instead, you create that shock wave. And this was actually inspired by shrimps. Some of these shrimps have got a species of shrimp, and they have these massive claws. And they stun their prey by just snapping their claws really quickly, and it creates a bubble and a shock wave. And that shock wave is really intense, and it stuns the prey. Well, the physicists were inspired by this, and they use a projectile that it hits another projectile, creates a similar sort of shock wave. And what it does is it hits a little bubble of fusion fuel contained in what looks a bit like an ice cube. And then that causes the fuel to implode, and you get fusion. So it's really sort of exciting, and this could potentially be a simpler way to fusion, and simpler means cheaper, and it could be implemented more quickly.
So, I mean, they were able to do that with this tiny little peppercorn-sized bubble of tritium and deuterium, but it took them, I don't know. I don't know how long it would take to reload, but they would have to do this many times a second, wouldn't they? Really, to actually, for it to be feasible commercially.
Yeah, and that's the sort of limitation of the National Ignition Facility. They did it once, and then they would have to, they only ever did one shot a day. And if you're going to be a commercial power plant, you'd obviously be wanting to do this, many times per second.
And I read somewhere that the actual peppercorn-sized pellets cost about $30,000 each, because they have to be so fantastically spherically symmetric, and that's very difficult to do. So they haven't really, cracked the problem of actually, creating these pellets properly. But the other thing I read, which you may know more about, is that they only got more energy out because they ignored all the energy they put in, and they actually just compared it to the energy of the lasers that actually touched the pellet, and that 99% of the energy they didn't actually account for. So when you account for that, they actually got out very much less than they put in. Is that true, or am I just being very cynical?
No, you are right, and I think that there's some things to say about that. So first of all, you are correct, but bear in mind this is an experiment,
Yeah.
and I think in terms of like a proof of concept, this result is huge. It's really significant result. The challenge for fusion now is we have to make it commercially viable, and that is one heck of a challenge. Those lasers that were used at the National Ignition Facility, they were designed and developed decades ago, and laser technology has come on leaps and bounds, and there are some new fusion startups that are looking at doing this much more cheaply and on a much smaller scale, and much more and sort of a higher repetition rate as well. But that is absolutely the challenge for fusion now, is to make it commercial.
So this is they really, it's an important step along the road to commercial fusion. This is called inertial fusion, isn't it? This laser.
Yes, that's
fusion.
Right. Yes.
But there's quite a few steps to go. So now back to Tokamaks, which is now there was some major development with Tokamaks in the last year and a half. Can you tell me that? Yeah.
So 2022 was quite the year for fusion. That it ended on a highlight with that result from the National Ignition Facility. But at the start of the year, there was a big announcement from Tokamak, and this machine jet produced the highest, the sort of produced a record power from fusion energy. So it was a real record-breaking shot. And I think, Marcus, you might have a video of it.
I think I have. Just a second. So let me see. No, the video seems to have gone. Just a second.
So while Marcus is looking for that, oh, here it comes.
Really? Oh, fantastic.
Here we go. I can hear it. So did you see?
So that by the way, that is a plasma of 100 million degrees in the Oxfordshire countryside, and I think, Valerie, you said there are cows grazing in the fields around where you work. And why was it pink?
So what you saw was you saw when that pink lit up, you could see these tiles and this curved shape of this machine that I'm Tokamak that I'm sitting in. But the pink color comes from it's quantum mechanics. It's all to do with the energy levels of hydrogen and the sort of quantum levels in hydrogen. And so the light that gets released is there's blue and red, which it gives you that pink color. So it's to do with the energy levels in the hydrogen. And the pink bits that you saw, that's the cool bit of the plasma. That's the colder bit of the plasma that you saw at the edges of the wall and at the bottom. The really hot bit is so hot that it glows in it glows in X-rays, and so it's not visible.
Presumably, there's nothing as hot as that within many light years of the Earth. That's the only things I can think of.
Yeah, I mean, Cullum is the hottest place in the universe. Yeah.
Okay. Unless you're in the accretion disk around a black hole or something like that. So it's the hottest place for a long way, isn't it? How many grams of or how much tritium and deuterium was actually used?
It's tiny amounts. It's at the level of grams.
And they were able to maintain this temperature for, I think it was 5 seconds. Is that true?
Yeah. Yes, that was 5 seconds. Now the reason for that 5 seconds, I know that may not sound impressive. That was only 5 seconds
compared to those laser people. Because I mean,
Yeah,
it's just only a short time, wasn't it?
So, so it's the time the 5 seconds. The time was limited by the magnets and the magnetic field. So remember, I said that there were magnets surrounding this tokamak and holding that plasma. These are electromagnets. So it's coils of copper. And you pass an electric current through it, and that creates a magnetic field. Now, when you pass the current through that copper, it's a bit like old-fashioned light bulbs, where they would glow when you passed an electric current through them. You pass this current through these copper magnets, and they were in danger of like melting if you put the current through it for longer than 5 seconds. So that's what limited the time there. But for the next generation of machines, these are going to use a new type of magnet made of superconductors. And one of the really sort of clever and smart things about a superconductor is that there's no electrical resistance. The current flows through without any electrical resistance. And why that's important is that the magnets don't heat up in the same way. So you'll be able to operate these magnets for a lot longer. And they'll be able to produce even higher magnetic fields. So they'll be able to increase the power of the plasma as well, and of the amount of you'll get a greater fusion power using these superconducting magnets as well.
So the key thing about maintaining this 100 million degrees for 5 seconds was that more energy came out than was put into heating the plasma. I mean, can you put in perspective? I mean, how much energy? I mean, how many kettles could we have boiled?
Yeah. I think that's not really the way I like to think about it, because it doesn't sound very impressive. And again, the thing to stress is that JET is an experiment, so it's not JET wasn't designed as a power plant, and it took more energy. You had to put more energy in than you got out in this case. So it wasn't designed for this experiment wasn't designed for energy gain. So just have to stress that that was sort of the experiment.
So what was the key thing about this development? Was it that maintaining the plasma for 5 seconds? Was that?
Yeah. So it was that, and it's the record amount of energy that we got out as well. And again, I sort of stress that point that we were making earlier about the promise of fusion is the amount of fossil fuel that it will displace. 1 gram of hydrogen versus 10 tons of coal. Yeah.
So you mentioned earlier that there is going to be a successor experiment in France. I think it's called ITER, is it? ITER?
ITER, yeah. So it's with a French accent, ITER.
Okay. Whereabouts in France is it?
It's in Cadarache, which is in the south of France, near Aix-en-Provence.
Oh, lovely place. So
you should, yeah. I haven't been yet. It's one place I haven't been, but I think it does Aix be very nice, I think.
Aix-en-Provence is a beautiful town. So this is going to be significantly bigger, I imagine. You're talking about this Tokamak being 3 meters across. Presumably we're talking about something significantly bigger than that.
Yes, yeah. So the plasma volume of JET is 100 meters cubed, and it's going to be nearly 1,000 meters cubed inside ITER, and the radius of this is going to be is double. And then when you add in all the size of the magnets, then it is absolutely colossal machine. Everything about ITER is just on a grand scale. The size of it, the complexity of it is, I worked on complex particle physics experiments, but ITER is taking it really to another level. And the other challenge with ITER is it's a big collaboration involving many countries. I think when you add up the population of all the countries involved, it's more than half of the world's population is sort of covered by ITER. And all the components from ITER are coming from these different countries. So the physics is complex, but the logistics are complex. The politics is complex, and this is just, it's just a sort of really monumental machine.
And it's an experiment still.
It's still an experiment, yeah.
One more step on the road to a commercial reactor, but so there are a lot of more problems to be solved. By the way, I forgot to ask you about, is it true that fusion doesn't produce much in the way of nuclear waste or dangerous nuclear waste? And is it true that it doesn't produce greenhouse gases? So are those two advantages?
So it doesn't produce greenhouse gases at source. So you don't get greenhouse gases in the fusion reaction itself. So what happens is, I talked about when you have these variants of hydrogen fusing together, what you get, this neutron that comes out, and that neutron travels out and it hits the walls of the Tokamak.
It's not contained by the magnetic field because it's neutral.
That's right. It escapes the magnetic field, and that's exactly what you want. And then when this machine is, if the power station version of this machine will be surrounded by this lithium blanket. And we talked about the lithium blanket being used to produce the tritium fuel for the next reactions. But what that lithium will also do is it will turn that neutron's kinetic energy as well into heat. And that heat then goes on, and all very sort of very traditional after that. The heat that you get coming out will then go on and heat up water. The water turns to steam, the steam turns to turbines, and then you'll get electricity coming out. So all very conventional after that. The clever bit is...
we should emphasise that all we're doing is boiling water. This is a very, very complex way to boil water.
It is, yes, it is. It's a complex way of boiling water, but we've been boiling water for many years, so I think which should give us confidence that that we could have a fusion power plant. But going back to what happens with this neutron, when it goes through the walls of this machine that you see, the neutrons can knock atoms out. But it can also, the other thing that it can do is it can react. It can have nuclear reactions with these walls as well, so that you start off with a steel vessel, and what you might end up with are these nuclear reactions happening and transforming some of those the elements that make up steel, transform them into other kinds of elements as well. Now, some of those elements might be radioactive. They go through a radioactive decay process. So this machine, when it's finished, will have some radioactive elements in it. The thing that's very different about fusion and fission, in a fusion reaction, it's really hard to get the fusion reaction to start. And if there's any sort of disturbance to it, then it just goes out. Like you saw with the that reaction you saw just lasted for 5 seconds. It's almost like sneeze and the thing goes out. You cannot have a Chernobyl style meltdown like in a fusion machine, but there will be some radioactive waste, but all the calculations show that that's going to be intermediate level waste. And
does that fusion mean it's short-lived? You mean it won't have long half-lives? Is that what you mean?
It won't have long half-life, and all the calculations show that that fusion presents less of a hazard than fission. And in fact, this is where the UK has taken a lead, and the UK government has produced some regulations for fusion, and they're different from the regulations that you have in a nuclear reactor, and that reflects the lower risk that fusion presents. And those regulatory changes are really important for a couple of reasons. I mean, it reflects the fact that fusion it poses less of a risk. But what that also means is that you don't need to over-engineer. If you just took, for a fusion machine, if you just took all the regulations, all the concrete walls and the steel shielding and all the things you need to protect you from a fission reaction and applied that to fusion, what you would be doing is like completely over-engineering the machine and the power plant. And it would be excessively expensive for what was needed, and it would take longer to build than what was needed. So, when I first heard about regulations, I thought, oh gosh, isn't that boring? But actually, it's a really exciting and important thing, and it's something that the UK is taking the lead in, which might be a surprise to some people. And many people around the world are looking at what we're doing in the UK, and really wanting to follow what we're doing here as well.
I mean, presumably the neutrons don't just produce radioactive nuclei; they weaken the structure as well.
Yes.
Yeah.
And a big focus of the research at the moment is to find new materials and new types of steel that will be resistant to those neutrons, because as you say, those neutrons could weaken the steel. It's a bit like if you put a plastic Tupperware box outside, or plastic box outside on a in the garden for several years, and you come back and you discover it's all kind of disintegrated because the sunlight sort of weakened it. Similarly, the neutrons would weaken the steel, but there's a massive research program going on looking at materials. And also another thing that we're working on here at the UK Atomic Energy Authority, as well as researching those new materials, is also a big maintenance program as well. And it uses robots. So rather than send people into these machines to replace these things behind me are these tiles that you can see. Rather than send a person in with a screwdriver to replace these tiles, what we do is send a robot in to replace those tiles. It's not quite a robot. It's a special arm that goes in, and there's an operator sitting in a control room well out the way. They're almost like wearing an exoskeleton, and I don't know if you've seen Dr. Octopus from Spider-Man. The operators there in a safe environment, using sort of screwdrivers and manipulating their arms like this, and this remote handling. And inside the Tokamak, you have these robot arms that are mimicking doing exactly the same thing inside, and everyone's safe. And so that's really, it's actually a really fun thing to see. It's one of the really fun parts of working at UKAEA. And that technology is actually being used over at Fukushima as well. So that sort of remote handling equipment and these robots, the research work that's been done here is now finding its way over to Japan and to Fukushima, and is helping in the cleanup operation there.
So Fukushima was where the tsunami caused the meltdown of more than one reactor, I think, wasn't it? I can't remember. Yeah. So, what are the major problems that we need to solve before we get to a commercial reactor, and what kind of timescale are we looking at for that to happen?
So we've talked about materials being a thing, and there's a big active research program going on there, and we've talked about the tritium as well. I think what's really exciting for me is that many years ago, like when I started at New Scientist, I used to come here to Culham and come on lab visits, and this was very much a place of science, a place of science experiments. And what we've seen over the last probably five years, I mean 10 sort of 5 years, is we're seeing these startup companies now that are working in fusion. And I think that's a real game changer. But these startup companies have got really ambitious timescales, and many of them predict that they will get fusion energy onto the grid in the 2030s. The UK.
Away. I mean, obviously you'll hate me mentioning this, but the joke about fusion is always that it's 50 years away. It's always 50 years away. You're saying that it's not 50 years away anymore. It's 10, 20 years away.
Well, I mean, we can't say for sure. So, but the thing I can say for sure is we've never been closer to fusion energy. I think so. The private fusion companies are very bullish about their predictions of when they will get fusion energy onto the grid. And I think someone will demonstrate it pretty quickly. But bear in mind, that's not the same as suddenly being able to switch on your kettle and it's powered by fusion power. But I do think someone will demonstrate fusion energy, getting it onto the grid quite quickly. I mentioned the UK and the regulations. What the UK also did recently was the UK government has published a fusion strategy, and part of that fusion strategy is to build a fusion power plant, and which will be operational in the 2040s. So that's a bit longer than the private fusion companies are suggesting. But it's going to be really interesting to see what happens there. There's a site has been selected for this. It's in West Burton, which is in West Burton in North Nottinghamshire. Let me get that right. I get my norths and wests mixed up. So West Burton in North Nottinghamshire, and there at the moment it's the site of a coal power plant. So we're going from fossil fuels to fusion fuels. So it's really exciting that the UK government has this commitment to build this fusion power plant, and we have these private fusion companies as well. And you know, a lot of people, you know, in my old job at New Scientist, I would have been very much like pitching this as a race. You know, who's going to win first? Is it going to be the government programme, or is it going to be these plucky startups? And which one is it going to be? That's not really the way to think about it now. They're very much like working in tandem. The research work that's going on here, it covers that robotics, it covers the materials, it covers the tritium, and the private fusion companies, they don't have to solve all those problems at the same time, but they will be working with national labs in the UK and elsewhere on those problems. So lots of these public-private partnerships. So it's a really, really exciting time. And I mentioned to you, Marcus, that I think there are some parallels. So with space, because when I worked at New Scientist back in the early 2000s, we were hearing about these weirdo space companies, to be honest, and we thought, there are these people, a lot of them out in California, who were talking about sending people into space. And you know, I remember thinking, why would they want to do that? Because this is what NASA does, or the European Space Agency, or China, or Russia. It's these national programs that send people into space. Why do private companies want to do that? And I think that these companies like Blue Origin and SpaceX, and what does Richard Branson think he's doing? Who is this guy, Elon Musk? You know, and then fast forward 20 years, and you see SpaceX sending astronauts to the International Space Station, launching their reusable rockets, making it much, much cheaper to go into space. And from my perspective, you know, I think fusion is at a really similar point to where space was in the early 2000s. That's what gives me, that's what makes me really excited about this.
So could it solve our global energy problems? I mean, presumably it's going to be, if it does work, it's going to be too late to have, sorry, to be the technology that helps us with cutting our greenhouse gases, because I mean, we're still talking about 10, 20 years away. But could it solve our global energy problems? And maybe 50 years ago, we didn't have all these alternatives like wave power and wind power. I mean, it's got to compete against them, hasn't it?
I hear what you're saying, Marcus. I think that it's really important to emphasize that this is not fusion versus renewables. I mean, look at where we are with climate. We need everything to, we're in a climate crisis. We need to throw everything at this. I think renewables are fantastic. When you look at all the predictions for how the global's energy demands and use are going to grow, it's a really steep curve. It's really, really steep. And renewables are advancing as well, but they don't seem to be advancing as fast. And then you have the issue of, well, what do you do when it's not windy, or when the sun doesn't shine, or if there's a drought and you can't operate a hydroelectric plant? So you have those issues, and so you want something that works at night, and so on, and fusion could do that. Someone put it to me, someone described it very succinctly to me a few months ago. They said that fusion may not help us get to net zero, but what it will do is it will maintain net zero. I think there's a tendency for a lot of people to think we get to net zero and then that's it. But the world's energy demand is just going to grow. You can see it as, more and more things are going into the cloud. We're electrifying more and more of our transport. And we want to pull the developing world, we want to pull their living standards up as well. So global energy needs are just accelerating. And I think this is where fusion can really, really help out.
Great. Well, what next for you, Valerie? Are you going to stay working in the fusion field?
I think so. I mean, I just finding it such an exciting space to be in. One of the exciting things, I love these big physics projects, and I love these things that they sound crazy on paper, and I think from my time at New Scientist has given me a lot of perspective. There were many things that when I started my career at New Scientist, I never thought would happen. I didn't think we'd detect an Earth-like planet. I didn't think we'd detect gravitational waves. I didn't think we'd have a quantum computer. And you cannot underestimate or write off the ingenuity of scientists and engineers. I mean, you might need to give them time and lots of money, but you cannot, write them off. And they will. Fusion will happen. I'm absolutely convinced of it. So yeah, I'm here to stay, I would say.
Well, I agree with you. I mean, there's never been a more exciting time to be alive as far as science is concerned, because, as you say, we've made all these major discoveries like gravitational waves and whatever. Perhaps we'll find dark matter next year. I don't know. The James Webb was launched only 18 months ago, and it's already showing us, the early universe that we haven't seen before. So yeah, it's a really exciting time to be around. Now, you've had a very interesting career. I wonder what advice you'd give to other girls who are interested in physics or interested in science.
I would just say, follow that passion. One of the reasons I decided to do physics at university was I was really excited by the science. I found it, absolutely fascinating. But also, you can do so much with physics. The skills you learn when you're doing physics, everybody wants them, afterwards. I sort of thought if you go and study, now I'm maybe being a bit unfair here, but I thought if you go and study dentistry at university, you come out and you're a dentist. Studying something like physics at university, you can come out and do, anything. You could even transfer to a dentistry course if that's ended up being what you want to do. So I would say follow your passion and don't be put off if you are the only girl in the room, which you sadly, girls are still in a minority when it comes to doing physics. Don't let that put you off. Use that as your superpower. You will be remembered, you will stand out. And so, yeah, just keep on pursuing that passion.
Great. Well, thank you so much, Valerie, for a really fascinating chat. I hope we've all learned a lot more about fusion. So thanks very much for giving us your time. And
thank you, Marcus.
It's really fantastic. And, join us again in a month's time, and we'll do this all again with another interesting interviewee. So until then, goodbye.